opportunity to give these lectures. And these lectures are meant for students, and I'm very, very happy to see some distinguished colleagues here in the audience. This is not for you, this is really basic things. So this is, so I hope you brought some work or some entertainment, and, or feel free to leave anytime. So the goal in these lectures is, at least in the first four, is to explain the following, I think, remarkable case. I mean, the results are not exactly new. They're close to 10 years old now, and this is there's a remarkable insight of Nekrasov and Tashvili identifies the following things. So on the one hand, one can take the quantum homology or K-theory of, let's take disjoint union from K to N of cotangent bundle to Grassmann variety that parameterize K-dimensional subspaces of an N-dimensional space. And so this is, what this is. So this is here, this is disjoint union of algebraic variety, so everything is going to be just independently. Every one of these will be not interacting with the other ones in any way. And so what this thing is this is a remarkable, this is associative, commutative associative. Commutative associative deformation of the ordinary cup product, Del. Distinguish ordinary cup product in the cohomology of each one of these varieties that depends on a variable z. There's one complex variable z, so that at z equals 0 you get the ordinary cup product and z something deformation. And that the fact that there is only one z is because there's the second homology of this is one-dimensional. So in general there's as many variables as the dimension of second homology here. And so what Nekrasov and Tashvili say that this is the same as a certain quantum integrable system. Namely, this is a certain integrable quantum spin chain. So I'll just write spin chain, some specific one. And what? So it's a quantum integrable system means there's a Hilbert space, vector space, and Hilbert space. And some operator. So the Hilbert space, it's a system of quantum mechanics. So this is just so the state of the system is a spin chain of length n, and it can have maybe I'll draw this. So it can have some spins down, spins up. So where the length of this chain is n, and k is the number of spins up. In other words, the Hilbert space is an n-fold. So each one of this is can be in two possible quantum states. So you take this two-dimensional space and you raise it to tensor power n. And k has to do with the weight. Well, it's not exactly the weight, but it has to do this number k. It has to do with the weight with respect to this SL2 or GL2 action here. So this is how many times I use one coordinate and how many times I use the other coordinate. So in this Hilbert space, I have a remarkable operator. Maybe I'll call it energy operator. This is just, so I'll state it in cohomology. So this is something very simple. So how do I, so this is essentially unique. This is unique possible U2 or SU2 invariant invariant interaction. If I'd like the nearest neighbors to interact, then there is in SU2 or invariant way, then the tensor square of C2 is a SU2 representation, has two reducible components. So there are two operators. There's identity and one extra operator. So identity is not interesting, and the extra operator is just permutation of factors. So this is summation over all I. 1 goes from 1 to n, and I just permute I plus 1. So if I want to describe eigenvector and eigenvalues with some operator, I'm free to add identity and I'm free to multiply by constant. It's not going to change anything. And up to this transformation, there is one and only way for nearest neighbors to interact. And you can ask, well, there's a variable z there. So what is the variable z doing here? And the variable z there, this corresponds to the fact that in this interaction, you see I've written it from 1 to n. And you have to specify, once you're at the beginning of this chain, you have to specify what sort of boundary condition you're going to impose. And you can impose, for example, the periodic boundary condition, but there are more SU2 invariant boundary conditions. There's more ways to impose boundary conditions. And, sorry, not SU2, but just there's more ways to impose the boundary condition. And the boundary condition we're going to impose that the n plus first space, so space SU2, the n plus first copy of that, this is identified with 1z. This is what's called the quasi-periodic boundary condition. So as you go around the circle, you get a phase factor in one of the entries. So, or n plus I. Say n plus I. I. And so now you can see why this probably hasn't been noticed before, is that here we start at the point, here the cup product, so there's a new product, so it's there's a new product, maybe call it star, alpha, beta, star. This is alpha cup, beta, plus all capital of Z, some series in Z. Which in general doesn't even have to converge. It's in general some formal series. In our case, it will converge to some very nice rational function, but it's some series in Z. In other words, this is somehow everything here happens around the point equals Z equals 0. Whereas here, the natural, when people think about this, they naturally first start with the periodic boundary condition. So this the basic point is Z equals 1, which is like the worst possible pole on that other side. And so, and in any way, this is when people in application typically Z is 1 or maybe root, or at least has absolute value 1. So that's they get really phased, and the fact when Z equals 0 is really bad because it's not invertible. It's not invertible. Yeah. So you really need to a full to see the identification. You really need you really can't see the identification by looking at the classical cohomology here, the classical coproduct here, and something there, because there it's z equals 0 is not really a value you can plug in there. And z equals 1 is really not such a good a value to plug in here. And so this is only beginning. So this is what I'd like to explain in this lecture, or at least in the first 4 lectures. And this is really beginning of the story. And this is already this somehow the outline of the story already present in the work of Negrad-Shadashvili. So that what's important about this variety. So this is an example. This is the simplest Nakajima variety. For any one of them, you can study its quantum cohomology. And what it will be correspond to? Well, there's quantum integrable system like this that you can express in the language of quantum groups. This is in some sense what the quantum groups were invented for. And so it's very remarkable that the quantum groups were also somehow. The Nekrasov-Shadashvili, they are offsprings of in some ways of this Russian, even maybe some I don't know, some Russian mathematical school, and there's always this wonderful interaction between Russian tradition and Japanese tradition. Like the quantum groups were very much born together at somehow the same time here in Kyoto and maybe St. Petersburg, and so there's a whole machinery of quantum groups how to explain quantum integral system like this in terms of quantum groups. And well, Nakajima varieties, one of the reasons they were introduced is to have a geometric picture for representations here of quantum groups. And so now now I'll explain. And another very important thing that we see here is that is something a very common theme in this kind of part of mathematics, is that here you have some vector space, some representation of subgroup, in fact realized. It's a vector. So you start in linear algebra, start with vector spaces. Here it's realized not as some abstract vector space, but geometrically as cohomology of some maybe K-theory group of some variety. But this is a sort of geometric realization of a problem in mathematical physics. This is very important, very valuable. Like for example, of course, for this particular operator, its eigenvalues and eigenfunctions, they've been computed many years ago. But this is essentially work of Hans Bethe, so this is almost 100 years old. So it's like maybe 1931 or some such in some very old times. But in general, if you have a geometric realization, maybe you'll get to this in like lecture 4. This really helps to find both the eigenvalues and the eigenvectors in problems like this. But so we'll start maybe slowly, so we have maybe we'll start with some variety X, and this would be for now would be smooth, maybe quasi-projective. Algebraic variety. So projective means it's closed in the projective space. Quasi-projective means an open subset of such. So e.g. for today, today we'll be only look at projective space itself or the Grassmann. This projective space being the case of the Grassmann with k equals 1. And then we look at cycles in X modulo some equivalence. And so this could be the homology of X. So this is, or since we assumed it's smooth, there's not so much difference between homology and homology. Or you can look at Chow groups. Or so the setting I like the best is really the K-theory group. Means if you have a closed subvariety in X, then the functions on that variety means you take all functions modulo those that vanish. This is a sheaf of this is a module under functions multiplication. This is such defines an element here. So this is maybe the best. This is I like the best this sort of setting. So you can consider various spaces like that, and they are arena. So this is so how will operators? So here, so this the setup of quantum mechanics is the space of space and some operators, and so how will some operators appear in the setting? So then. So this correspondences. So what's a correspondence? It's an object of the same kind on a product with X. Could be a product with X some other variety, but for now let's take with itself. So i.e. you can take homology classes or homology classes on the product with itself or elements Kx itself act on this. And so how does this, so let's say, how does a cycle on the product acts here? Well, it's so if I have a cycle on the product which I'll denote maybe M or matrix, it's like a matrix. And so if I'd like to apply a matrix to some element alpha, well, what do? I pull back. So from this product there are two projections. The first into the second factor. So I pull back under the projection to the second factor alpha. I intersect with M, and I push forward under the projection to the first factor. So here I use the fact, so I'm intersecting cycles because I can intersect cycles. Is it because I have assumed that my variety is smooth? Or if I had like a homology class, then I could take a cup product like a homology class. And so what does this concretely? So for example, the example which is so e.g. if X is a finite set, then the homology, well, it only has zero-dimensional homology, but so the homology of X is just really n copies of Z, right? The homology of X cross X, these are really matrices of size n with coefficients in Z. Well, I could I can consider some ring of coefficients, for example this, and this amounts to the ordinary multiplication of this will give you this ordinary. And similarly, if you understand how to multiply matrices, you immediately generalize this to how to multiply two correspondences. Another formula with which to compare is that if I have a kernel, so if I have a kernel is a function, k of xy, maybe x1, x2, is a function on f cross x, it acts by an integral operator, so it means I take a function f of x, I send it to the integral kx x2 f of x2 dx2. So this is in functional analysis, or this is very important. But this can be defined anytime you have a notion of product and pullbacks and pushforwards. You can define operators like this. So in this sense, cohomology or K theory and so forth of the product, they're really like they're matrices of the shape X, may be subject to whatever equivalence you impose on your cycles in the first place. And so now quantum multiplication is a deformation. So quantum product in usually people write it in cohomology, but you can define is an example this construction, or rather, not of this construction also, but in general, you can ask why stop at just two factors. You can have more factors, and then you have more complicated kind of tensors, right? So you can have, so you really, what you really want, you want a map from, what you want is a map from a new product. You want a cohomology of X, some new operator tensor, cohomology of X, some new product which calls star to go to the cohomology of X. And this would be given to define this. You need a cycle in 3 copies of X, not 2. And this is the way it's defined is this. Won't be a good notation. So I'll just copy what I wrote here. So you take tensor the quantum product alpha beta that will start with the usually cup product plus summation. So in general, you sum overall if all well, I already took, here already, we will see it, here I already took out the contribution of degree 0 curve, so you sum over non-zero degrees in this form, so this will be h in general and h lower 2x z non-zero. And in fact, you sum over only effective degrees, but we'll get there. And so then, in the case of Grassmannian or projective space, that group is z. So I can write one variable to the power z. In general, it's a multi-index. And then I'd like an operator defined by a correspondence. So an operator times an operator defined by the following cycle. So I need by the locus. So inside of the triple product, I look at the locus of points that lie x1, x2, x3 lie on a curve of degree d. We'll define this more carefully in a second, but this is the basic. This is the basic. So if I have on a rational curve. So for every this parameterizes among many other things. So if I have a curve, a rational curve, then its fundamental class defines for me an element here, and then I can. So this will go into this power of z, and then there'll be a correspondence, namely a triple of points that. More formally, if you want some more formal definition, why is this even a cycle? There's an evaluation map from here, from the moduli space, M03 bar x t. This moduli space is parameterizes is the following data. So an element of this moduli space is first of all a curve of at worst nodal curve of arithmetic genus 0. So I'll draw a picture, and I draw so there's one can draw a curve. Like a complex geometry will write a rational curve. A complex geometry will so maybe a complex geometry will draw a collection of bubbles like this, and so it has essentially some points. And so in algebraic geometry, it's more a tradition to draw a curve as you would draw a real curve. So it's something like this. So it has 3 marked points. So this is an example. Maybe add more components here. So something like this. So this is at worst nodal. Of arithmetic genus 0, meaning. So arithmetic genus 0 means it's a union of rational components that form there's no loops, it's formed a tree. So this is arithmetic genus 0 and 3 marked points. Then, so this is my curve C, and my parts point P1, P2, P3. Then the next part of the data is a map. Maybe I'll draw in some color. The next part of the data is a map f to my x. And this has to be a map of degree d, meaning f push forward the fundamental class of C equals d. This is an element in h lower 2 of x. That. And this evaluation map takes the f and sends it to the value at mark points, so f of p1, f of p2, f of p3. So the fundamental feature of this moduli spaces is that this map, well, if x is projective, that map is just proper. We will be, and so you can take, in the situation with projective space of Grassmann, you can take a fundamental cycle and of this modular space and push it forward. In general, so this would be that cycle that I'm talking about. In general, there are some other cycle. There's something more complicated called the virtual fundamental cycle, which is defined with great care and slightly differently in algebraic geometry or symplectic geometry. But that's for the examples here, you just push forward the fundamental cycle. That is the cycle product we want to use. So the remarkable feature of this look at my notes. Right, maybe I'll say it from the beginning is that the T-star Grassmannian is obviously not compact. It's not, but all varieties we'll ever consider, we'll have the property, and we will see it in easy consequence of geometrically very easy to see that in fact already the map that just remembers one mark point is already that's a proper map. So there will be no issues. Even though we know it's not compact, this map will be proper. Even the one with one mark point is already proper. So so why is this? Right. So maybe I'll. Oh right, I forgot to say one thing. This has to be this map has to satisfy stability condition. Means stability condition. That means that the two such objects are isomorphic if there is a map between the domains that isomorphism between domains of the map that makes the triangle. That makes the triangle. So in particular, for every map, for every such object, there's a well-defined group of automorphisms. Automorphisms of F. These are self-maps of the domain that commute with the map. Commute to the map here. Not commute somehow. Self-maps that preserve the map to X. And so this has to be a finite group. So this is finite. The dimension of this is 0. Right, better to say. Dimension automorphisms. F is 0. This is the stability condition. concretely, this means that any time, like this example, like if I look at this rational component, the component by itself, so if I have a rational point curve with one mark point, then this has a two-dimensional group of automorphisms. Here I have a rational curve with two mark point, has one-dimensional group of automorphisms. And so if I have something like this that has, then this cannot be contracted by the map F. In principle, some components of this curve can be contracted by the map F. But if only those that contain at least three special points, like this middle one can be contracted, like this one can be contracted by the map F because it has four special points. And then another thing I want to say that this is if I look at maps of degree 0, this is just, so how can I possibly have maps of degree 0? Then the only possibility with the stability condition is to have my three-pointed curve to be just really contracted to some point in X. The domain, if my domain has any branches, that will have, so when we had some branches like here, then there will have to be a component that has less than three special points. And so then would be, then since it has to be a map of, this has to be a map of degree 0. Since it has to be a map of degree 0, that's impossible. And so then that's the only possibility. So this modular space is isomorphic to X itself. And this map is just embedding of the diagonal inside the triple product. And if you think of what the diagonal does inside the triple product, then it really does, what sort of correspondence, what sort of operator the diagonal inside the triple product defines in this language, then exactly this is exactly corresponding. If I'd like to write the cup product, then it says, how can I write the cup product if I take three factors, from two of them I pull back classes, intersect with the small diagonal and push forward. That's the cup product. This is because the definition of the cup product is what's the definition of Kolmogorov-Alexander definition of cup product? If I take the outer product of classes and I pull back the diagonal, that's the definition. So this is really, this gives you this piece. And so this quantum product is clearly commutative. Because that cycle in the triple product is clearly symmetric under permutation, and remarkably associative. And the associativity is a simple property, but remarkable. And why is this associative? It's because what if I try, so if I want to compute alpha, beta, and then gamma. Then in this language, so what is it in the language of correspondences? What is the quadruple tensor that computes this product? Well, I can have a, so this has to do with maps when I have a curve that has two components. So one component can have maybe I'll draw two different components in two different colors. So I have a curve with two components, maybe it doesn't have to be, so one component three mark points. And this is where I take my alpha. This is where I take my beta, and this is where it outputs alpha star beta. Means I pull back with respect to this 2, and I push forward with respect to this 1. And then I have a curve with another curve, another component. Can also have some stuff. But so this is here I take alpha and beta, and I add gamma, and at my third point I get get my output alpha, beta, gamma. Is that clear? This is so when you multiply correspondences, so you're multiplying correspondences like multiplication of matrices. You have some index, like a lower, sum over indices. Means here we were pushing something forward and then pulling back again, and so this means I really have a rational curve which has which looks like this. And so this is the locus, and so this whole thing maps to X. So this sits inside M04 bar X or something, or D1, D2. So this has degree D1, and this has degree D2. And then here the degree Z. And this is the locus where, what is this, where is this locus, which one is this locus? This is so a moduli space, an element, this is like a moduli space of 4-pointed curves. So P1, P2, P3, 4, and this is my P1, P2, P3, 4. So I take inputs at P1, P2, P3 and get output at P4. And so this moduli, the way this moduli spaces are constructed, this maps to the moduli space of just 4-pointed rational curves, which is isomorphic to P1 by the cross ratio. In this map, once I forget the map to X, that these bubbles become unstable. I have to contract it. So, like for example, this would be like this particular curve. I will have to, this particular curve will go to this curve. So this bubble will need to be contracted. This bubble will need to be contracted. So I just get P1, P2, P3, P4. Okay. In this language, what is this isomorphism? This isomorphism, what's the cross ratio? Is we take, I take 3 points. I take them to 0. I can take them to 0, 1, infinity, and some point maybe call it lambda. If this is, so maybe this is P1, P2, P3, P4. And this is the case where P4 became equal. So this is the case, this is in this language. When lambda got here, this means lambda equals infinity case. So this product is computed from a cycle here, which is the fundamental cycle, the virtual fundamental cycle in general, intersected with the pullback of a point under this map. So you impose the condition. In other words, you fix the cross ratio of 4 points so that the fourth point and the third point, they lie on a separate component than the first and the second. Right? But in this picture of cross ratio, when lambda approaches 0, 1, or infinity, means these 2 points go on a separate component, like. And then now it's clear that if I take this, if I put these brackets in a different order, then all that's going to happen is some relabeling of this marked point. It just means I'm going to be pulling back a difference, but that means I pull back. It means I pull back a different point class. And of course, whatever equivalence relation you have, either homological or rational equivalence or K-theory, any 2 points on P1 are equal. And so if you pull back 1 point under this P1 or you pull back another point, you get the same. So therefore, these 2 cycles, well, not identical the same, they're equivalent under whatever equivalence you want to impose. And so this means but this means my product on cohomology, K-theory, or whatever, this is associated. This is taken in 2 different orders. And so, finally, what I'd like to discuss is grading. And this is a very important notion in what is the dimension of the cycle. So usually cohomology is graded. So when you multiply cohomology classes, the degrees add. And so there's a similar statement here that one needs to know the dimension of that cycle. And so what is this? So if I have what is the dimension? So if I have the tangent space, so first look at the tangent space at some map F to M03 bar xt. What is this? So what are the deformation of a map? Well, so for every point, so maybe I'll draw, since I don't want to go, be going back and forth from this. So this is my x. And I have a curve in x. So how can I deform this curve? So for every point in my curve, I can specify the direction in which it's supposed to move. So somehow this means sections of the pullback of the tangent bundle to x. This is saying I'd like points to move in some direction. Well, this I'm not interested in, I'm only interested in the image of this map. So when I was discussing this group, I was moving out by the automorphisms of the domain. So there will be, so minus the automorphisms of domain. And I can cook it differently. I can first forget the marked points and then add the marked points back, because this may be more general. So I have n marked points or some number. What's a good mark? What's a good number of marked points? Let's say n. Automorphisms of domain plus the number of marked points, and this would be so. So my domain rational curve, so this will be 3. And then so this is for 3 for m03. This will cancel out. So this would be so when n equals 3, this part will cancel out. And so then the question, well, how big is this? Well, so we can, so in other words, this is sections, and this is section, just algebraic geometers, right? H0 for sections. And how big is the space? And then, in general, it's like the hardest question in algebraic geometry, how many sections a bundle has. But in this case, for the case of the case I wanted to discuss today, for the case of projective space and generally Grassmannians, this will be unchanged if I subtract the first cohomology of the pullback, because this is 0 for Pn minus 1 over general Grassmannian Kn. And the reason it's 0 is because these are homogeneous spaces. They're vector fields on it that generate the tangent spaces. This means the tangent bundle of the spaces is generated by global sections. There's enough sections to generate the bundle. And this is a pullback of a globally generated bundle, similarly globally generated. And so if I have a globally generated bundle in P1, it has no higher cohomology. So this thing will vanish. But in general, so the way it's for general algebraic variety, such as the cotangent bundle, so we want to do cotangent bundle of Grassmannian. So cotangent bundle of Grassmannian, of course, with every tangent part, there'll be the dual cotangent. So whenever you have something positive in the tangent bundle, in the dual part will be correspondingly negative. So in general, this will not vanish. And then what you should consider is, instead of the actual dimensions, you consider the virtual dimension of that space. And then this is still, so for T star or Pn, this is 0 in general. Not 0. And then the algebraic geometers and symplectic geometers, they deal with this problem slightly differently. Algebraic geometers, they say, well, this space here has a nice deformation theory, in that you can describe locally around each point. You need so many equations. So many unknowns. to describe my moduli space locally near a point. And then, so if you have, so in other words, in a situation like this, there's a way to deal with this, like with excess intersection problem. Namely, while you may have too many equations here. It might be the case that they're not really independent. There's some dependency between this equation, and the actual dimension of your moduli space is larger than this. So the virtual dimension is always a lower bound for the actual dimension. And so this is because these equations there may be dependencies between these equations, but there's a way to define a well-defined K-theory class, or so on the moduli spaces. There's a way to define if you know the like, for example, suppose you have a section of a line bundle. If it's a non-zero section, that defines for you a hypersurface. If it's in your variety. If it's a zero section, you can still define a hypersurface as the just picks, somehow just is a representative to the first Chern class of your section. This is well defined in whatever theory is somehow defined, well defined in Chow, well defined in homology. And so similarly here, if you know just, what sort of thing your equations cutting out your moduli spaces represent, this gives you a way to define a well-defined cycle on this moduli space, or a well-defined K-theory class on this moduli spaces. That will be a well-defined up to whatever equivalence relation you consider. For example, well-defined as a homology class. And that will have this dimension, and you take the push forward under this map. So now we have to see what this thing, right. And so this cycle here will have this dimension. All right, we didn't finish the computing. So dimension. What is the dimension of H0 minus H1? Well, this is Riemann-Roch. Says that this is the rank, so maybe I'll write H0 pullback minus H1, the same thing. So this is by Riemann-Roch. This is the rank plus 1 minus arithmetic. Oh, sorry. Not like this. It's degree. Right. Degree plus the rank times 1 minus arithmetic g. So this is arithmetic. And so this is we decided this is equal to 0. And so the rank of the tangent bundle is the dimension of x. And the degree, what is this? The degree of a pullback of a bundle. This is just the pairing between the first Chern class of the tangent bundle, which I'll abbreviate to the first Chern class of x. First Chern class of x is the first Chern class of degree tangent bundle. You pair it with my degree class. Right? And so the conclusion from this formula, so conclusion, quantum cohomology is graded. Graded if we assign the degree of z to the d to be this number. In other words, if we give the variable z the degree c1, then this would be a graded problem. All right, so this is in the remaining half an hour of this lecture. No, an hour. I have an hour. Oh, okay, good. Oh, I was worried. And maybe there's some, maybe that was going too quick about this. Is that maybe there are questions? Anyway, there'll be some, I'm going to write some problems for the lecture, and then be good if you haven't seen this before, it'd be good to learn the material to work through this, and then I think you can. And certainly easy to verify. So if I have a cycle of a certain dimension, and this is if this variable has exactly that degree, then this operator will have the ordinary multiplication corresponds to the small diagonal inside the triple product that has dimension x, and here to the dimension x we have this, and so then you have to compensate to this number. You have to compensate by assigning the variable here. Okay. So for first computation, let's do quantum cohomology. Of Pn minus 1. Well, maybe first, what's the ordinary cohomology of Pn minus 1? The ordinary cohomology of so Pn minus 1 so Pn minus 1, which has homogeneous coordinates, I don't know, W1, Wn. So this has a cell decomposition, so starts with Cn minus 1, where this is where W1 is not equal. Well, whatever you feel. So then a fine space of that dimension where this is not 0, and then Cn minus 2, and this is where W1 is 0, and W2 is not 0, and so forth down to a point, which is the point 0, 0, 1 in homogeneous coordinates. Shall we make a quick break, or no? You guys need a break? Okay. So, sorry, but it's not. Okay, maybe it's not super interesting, you know. But so it's corresponding to this, the ordering cohomology of projective space. This is even the z coefficients. This is the. So this is the class of the closure here. So there's inside. So W1 equals 0. This is a hyperplane. P minus 2 inside P minus 1. So this is the hyperplane. The class of that hyperplane is H. So this cell corresponds to H, next cell corresponds to H squared, this cell corresponds to Hn minus 1, and the H to the n is 0. Maybe I'll write it. So maybe and so now I look at so I compute the virtual dimension. What's the first? Right. So the first Chern class of Pn minus 1. What is that? Everybody knows? Raise your hand if you know what this thing is. Okay, well let's compute it. What's the tangent? So on Pn minus 1 there is so if you think of this as Grassmannian of 1 n, then this means there's a tautological subbundle. So on this there's tautological line bundle. Maybe I'll call it L, which is a subbundle in the trivial bundle of rank n, which is given by the fiber of the line is line itself. And so this is, in fact, in usual notation, this is O of minus 1. This is the coordinates on your original space, they're the section of the dual bundle. Like, for example, this is a section of this W1 is really a section of the dual bundle, a section of O of 1. And so then the tangent bundle to projective space, I don't know why I wrote 10, but it's the tangent bundle. It's the same as T. What is it canonically? So if I look at so I have a line, and what are the deformation of the line? Deformation of the line are just graphs of maps. So so if I have a Cn mod L, so the deformation of a line is a graph of a map from L to here. So it's a home from L to C and mod L. Maybe. So now if I expand this out, this would be, so this is a trivial bundle of rank n, and this is a trivial bundle of rank n, and this is my O of minus 1. So I get home from O of minus 1 to Cn minus home from, well, I'll just write L for L because it's shorter than O of minus 1, O of minus 1. Homes from a line bundle to itself, this is a trivial bundle. This is trivial. And this is n copies of O of 1. And so the first Chern class of projective space this is the determinant, the tangent bundle, and so this is trivial, and this is n copies of O1, so this will be n times the first term class of O1. Whereas the first term class of O1, this is this, right? Because this section, this is the first term class of O1. So this is n times the hyperbolic section. So then this means that the virtual dimension of m bar 0, 3 dn minus 1d, this is a dimension of x which is n minus 1. Want to make sure I multiply the numbers correctly. Yeah, so n minus 1 plus d times n. And so for d greater or equal than 2, this is number, this is greater or equal than 3n minus 1, which is bigger than 3 times the dimension of x. So remember, we're looking for, in a triple product, we're looking for a cycle of this dimension. Well, there's no, for curve of degree bigger or equal to 2, there's just no place for this cycle. Therefore, it's only, so what survives are only the constant map and the line. Remember, only terms with d equals 0 and d equals 1 do not vanish. And this gives the ordinary cup product. It's ordinary. And this is what's the map? What's the cycle that? So this is, here I'm looking for triple of points, so maybe this is my projective space. Yeah, minus 1. And I'm looking for triples of points that line a line. So if I have h, like for example, if I have let's start with a point. So if I have like h n minus 1 star product h n minus 1. So it's, in other words, this is a class of a point. It's a class of a point. I'm looking for a star product. And so then this is, so if this point is fixed and this point is fixed, and this remaining point is just, its only option is to run along the line that joins these 2 points. Okay? So this would be, so the cup product, first the cup product, and that is 0, of course. 0 plus z times the class of a line is h n minus 2. If you take a quantum the class of a point, you get a line. So this is the right equation. And in general, so if I take h n minus I star h n minus j. Then what will happen? So here could be the cup product, which means I'm gonna get h with respect to the cup product. These two things just add. So I get 2n minus I minus j, and this is non-zero. This is not zero if I plus j strictly less than what? Than 2n. Than n. Sorry. Because h to the n is already 0. Or you can get a term which is a line. So then if I have something, this is something of how to say, this is like gonna be, so if I have something of dimension, if this runs in a linear space of dimension of a certain dimension, and this runs in a skew vector space of a certain dimension, that all possible, so this is like, so if this runs in some vector space and this runs in some vector space, then all possible joins of these 2 points will strip a vector space of again a vector space of a certain dimension. And the dimension of that vector space obviously is, which I'm just going to copy here, it's just going to be, so in fact it's just this same minus n, so it's going to be n minus I minus j. And this is if I, this is the opposite, this is if I j greater or equal than n. So this is complete description. And so in particular, this ring is still generated. This was a ring generated by one element, H. And so after deformation will still be generated by one element. So the generator, huh? Maybe. Oh yeah, maybe this is right. So this is less or equal, and this is greater. Yeah. So thank you for. So in particular, so the generator H acts in the basis 1 H n minus 1 by the matrix. So previously it was acting by this principal nilpotent like this. But now if it gets to the last one, instead of giving you 0, it's going to give you z here. And so it satisfies, instead
z to the h equals 0
satisfies h to the n equals z. At least we can see we did this thing correctly, because both at least are graded equality. This has degree n, and this has degree n, and so it's at least this is correct. In other words, the cohomology, when you deform, when you start with classical cohomology with this ring was generated by one nilpotent element, and instead you go to instead of having a point of thickness n, you go to this, instead of having very thick point at the origin, you get this kind of root of unity type of spectrum. Right. So now I'm gonna go it's not difficult to compute similar for Grassmannians, but maybe I'll just state the answer, because we'll compute the more general answer anyway. So how does this story generalize for Grassmannians? So first, Grassmannian Kn. Well, you can use similarly like the projective space is the quotient of non-zero vectors by the scaling. The generalization is Grassmannian, so this is the quotient. One way to think about it, you look n times k matrices. Instead of vectors, you look at matrices. Instead of them being non-zero, you look of rank k. And so the span of the column of this matrix, that's the subspace of k-dimensional subspace in an n-dimensional space. So this is, I'm confusing big and small n's. So maybe I'll write n. And this is taking the module of GLK action, which acts in the columns of this. So this is Grassmannian. And this has a decomposition, the generalization of this decomposition here. One way to think about this decomposition, these are really the orbits. These are the orbits of the unipotent group formed by G. You take all lower unipotent matrices inside GLN, which acts on this space, and then if you it's elementary to see that this is these are the orbits. And the first, it says whatever the first non-zero element is the orbit. And similarly for Grassmannian, there's a similar classical the Schubert decomposition. So they say unipotent matrices orbits unipotent matrices. There's a similar picture to that. Namely, you look at the, I'll draw it like this. There, you were looking for the first coordinate that's non-zero. Here, you look for the first row of this matrix, which is non-zero. Let's say the first row of this matrix is, say, 0, but then the next one is non-zero. Then by the action of GLK, you can make any non-zero vector to be something like this, 1, 0, 0, 0. And then after a while, so then there could be the case that there's some vectors that are linearly, then the next vector is still linearly dependent on this. It could be that the next vector is not linearly independent on this one, so something of this kind. But that this star you can precisely, so I have my orbits of unipotent matrices, that this star here I can precisely compensate by the action. The star I can make 0 or any other number by the action of this element here. And then we'll come to the next, well, maybe I'll use this red for this and yellow for this. 1, 0, 0, 0, 0. Then will come a row which will be linearly independent of this one. And so then by the action of GLK again, I can make that row to be the second basis element. Something like this. And then if I get another row which is linearly dependent on the previous one, this means I'm going to get something of this form and something of the other form. This is where these entries I can make anything I want by the action of the corresponding unipotent. And then at some next point will come a vector of this form. And so I think you get the picture. So this says that the orbits of this unipotent matrices, they're still affine spaces, and their spaces they're indexed by the following data. One way to index them is you take this table. So this was an n by k table. And you take this table and you throw out all the red stuff. You compress. And you get so this would be n. So they're exactly the red rows. They give me a basis of a k-dimensional space. So this will be n minus k by k picture. That will look like 0, 0, 0, 0, now star. 0, 0, 0, 2 stars. 0, 0, 0, etc. And the way to think about it is to think of this as a partition, maybe in fact a couple of complementary partitions. So a staircase shape, something like this. That's where you can take either the zeros or the stars as a diagram of a partition. So this is a partition lambda that fits inside. Usually the diagrams of a partition, we would like to draw them horizontally. So maybe this is maybe I'll take it. It's not super important, so maybe I'll have like my lambda. So this is my k, minus k. This is my lambda. So this has a cell decomposition indexed by partition that fits inside a k by n minus k box. So, and this is each cell is a linear space. A dimension. The number of boxes in this partition. And this is one description. It gives you gives you an additive description of the homology. Right, so this is, we take, in this lecture, if we have an algebraic variety, when we'll talk about the homology, we take a complex point with algebraic variety. So this is the cell decomposition into complex cells, and in particular all the boundary maps are zero. So this gives you an additive bicyclic homology. It's called Schubert cells. If you'd like a multiplicative decomposition, you take, so there's, it's going to be one of the homework problems to prove that the to prove that the homology of Grassmannian is generated by the Chern classes of the so over the Grassmannian you have a tautological so if I have a linear space, we call it whatever. So the column span of this matrix is some linear space V. This is a V-dimensional space. I denoted previously L there for projective space. Vk inside Cn. This is the tautological rank K vector bundle. Chern classes of V-generic homology. Well, in fact, better take V-dual, because by the same reason here, it's better to take the first Chern class of O of 1 than O of minus 1. So maybe i.e. there's a surjection from, we take, even with integer coefficients, we take symmetric polynomials in k variables. So Chern classes of a vector bundle of some rank k, you think as symmetric polynomials in k variables. And so then it's a classical problem, which again, we will solve. It's easier to solve a more general problem than this one, but it's true that the Schubert class is represented by a specific, there's a specific very nice representative for in this description. So for the closure of the Schubert class is the closure of the Schubert cell, the same way as we take closures for projective space, and this is corresponds to Schur function. Lambda in these variables x1 through xk. And what this thing is the ratio of two determinants. So you take the determinant. So this when you when you write the partition, it's row length. It's row length of the usual unit line 1, lambda 2, so forth. You take the determinant of xi lambda j plus k minus j divided by the product of. So it's a classical fact in representation theory that this is a polynomial, because this is antisymmetric, and every antisymmetric expression in X, if I have antisymmetric expression in two variables, that's divisible by their difference. And so in particular, this antisymmetric polynomial is divisible by this antisymmetric polynomial, and therefore its ratio is a polynomial of this degree. It's easier to prove a more general theorem, which we'll prove later. And so now the quantum cohomology. So the quantum cohomology is best described just by saying that this is so maybe right. Sorry, I don't want to jump over something I've neglected to say. Is that in fact, the kernel of this surjection is the I have a symmetric polynomials. And the kernel is spanned by Schur functions that don't fit inside my box. So by Schur functions. And lambda where lambda does not fit inside. So this box is denoted traditionally as partition K repeated n minus K times. And is an ideal this is generated by the Schur functions corresponding to just one row, where that row the length of that row, it's enough to take it from n minus k plus 1 up to n. This is some ideal in here, and this is just some particular set of generated values. So obviously, this is if k equals 1, this specializes to previous description of a projective space. And now the quantum cohomology. Has a remarkably simple description. Namely, all you do is the following. You can think of this. So previously we were looking at So the spectrum for projective space, the spectrum of ordinary cohomology was some big nilpotent, some nilpotent thing, and the spectrum of quantum cohomology that was just n n. So I'll draw this picture. So if I take the spec of ordinary cohomology of projective space. So this is some big fat thing, and if I take the spec of quantum technology. So this has this. This sits in roots of unity. I mean, not the roots of unity, but this is like x. This is h to the n equals 0. This was h to the n equals z. Similarly, a similar thing will happen here. This is the map. The map. This slightly complex. I mean, this map will have just description. You take axis. So we will. Well, I'll give you the answer, and then you'll see. So this you take the set. Maybe I'll take this. So the spectrum. I just tell you the set, the possible values of x's. So this will be the sets of x1 through xk. Each one of them to the power n. Each one of them. This is there's some sign which I won't get correctly. So this is minus 1 to the power k and z. And they are distinct. So there's n choices for each x, but they have to be distinct. So there's n choose k isolated points. Right? So this is at least if I'm telling that the spectrum has to be discrete, then at least the number of points there has to be the dimension of the space, right? So the dimension, how many partitions fits inside in this box is the number of such partition is n choose k. Is that clear? Because one way to prove it is that so you can think of the partition as I'll think of them like think of this path here, so like a path going here. This path in total makes n steps, and out of n steps, k have to be vertical, and n minus k have to be horizontal. And so this means out of n steps, I have to choose k that go up. So this is the number of this, and choose k. And so this is a zero-dimensional set of this cardinality and this is a deformation of that, right? So this is, and the remarkable fact about this is that on this set, obviously, if I take a Schur function, so if I take S as a remarkable property, if I take a Schur function, then this I can define. This can be defined for arbitrary. Well, in general, you don't need to. You don't need lambda i's to be ordered anything like this to define this function, right? So this can be defined for arbitrary collection k tuples of integers. This is from its formula, it's anti-symmetric in the variables lambda I minus I, or lambda j minus j. So this expression here, it's anti-symmetric in the indices I and also anti-symmetric in the indices j. And so in these variables, it's anti-symmetric. It means concretely that if I have a and then, right, if I have a like S, I don't know, say 3, 0, this is minus S, well, let's see, so what's it going to be? So this is 4, 0, 4. Minus 1, 4. Something like this. So in particular, if it has two values that differ by 1, so if I have s of anything, and I have like, I don't know, 5 and 6, and this is 0. And then also on this, it's also periodic with period n. So also depends, only depends on lambda mod n. Well, up to a sign again, because up to a sign, since lambdas, if I take each, well, up to a sign in the power of z rather. Right? So maybe I'll write it like this if I take. So maybe I'll write what I want to write here. That if I take s and there's some entry, I take lambda I. This is lambda I plus n. This is minus z to the power k s lambda I. Because this will be each one of my variables raised to the power n gives me minus 1 to the power. Minus 1 to the power k minus 1 times z. In other words, if I want to compute now in this ring, it's in fact in some sense easier than I compute the ordinary way. So I get some expression in Schur functions. Then using this rule, I can always, so any expression in Schur function, I can always bring it to maybe better to think about like this. If I take I take the collection of integers if I take this set lambda I lambda j plus k minus j, this is a k tuple of distinct points for a partition. If lambda is a partition, then this is by the same argument, because what are these numbers? These numbers are the positions of the times when I take this vertical step. And so this is a k tuple of distinct points of in 0 through n minus 1. And so this says that every time I can associate a Schur function to a k tuple of not necessarily distinct points. So in principle, can associate Schur function defined for any k tuple of points in Z. But then if some points repeat, then this is 0, and if it's like this, and if they don't fall inside 0 through minus n, then I can use this rule to make them fall inside 0 through n. So this inside bound means the computation in the string are gonna vary. Take the following thing: you multiply in the usual way, and then you use these rules to reduce. This is what's this is what's called like Rim-Hook algorithm or something, some name like this, I think. There are many proofs in the literature, but we'll give. And right, and so but we'll see this as a special case so the quantum cohomology for T-star Grassmannian strictly generalizes quantum cohomology for Grassmannian, so we'll see this rule as a special case. And so now to right, I think I want to right. So as an example, let's see what this thing says for. Maybe let me just state that the results of the new relation, in other words, equivalently, you can the new relations are that the this short function is still it's still 0, because if I put this L, so what does this corresponds to where L, so this where this corresponds to what? This corresponds to my set here is like this. It's like L plus K minus 1, and then we get and then all the others are 0, so K minus 2. So forth. 0, 1, 0. And so there are two cases. So this number, so L in my notation is greater or equal than n was sitting between n and n minus k plus 1. So if I like, for example, if L is n minus k plus 1, then in this expression I'm going to get n. And modulo n, this is going to be the same as 0, so I get two repeated things, and that's therefore 0. If I we get two repeated indices. Right? I mean, in this range of parameters, it's clear that the only time I can get modulo n something different, since this is then with this number L is exactly n, right? Because then I get modulo n, I get k minus 1. Otherwise, I get something which I already previously had. And I apologize. The basic combinatorial problem is too late in the lecture. It's not. Right? So this is this said that this thing is this thing. Maybe I'll erase. Maybe I'll copy this here. So my lambda I minus lambda j plus k minus j. This is the set L plus k minus 1 and k minus 2, so forth, 1, 0. And so this is 0 if minus k plus 1 less or equal n. And that's strictly n. And then if L is n, then by that rule, I get minus 1 to the k minus 1 times z if L is equal to n. Because then you get the Schur function. By this periodicity, you get the Schur function for the empty partition. Schur function for the empty partition is 1. Okay? All right. Looks like I've so maybe to summarize. What would be the description for the what would be the description for a quantum cohomology of the cotangent bundle for Grassmannian? Something very similar. So it's again will be generated by some universal expression. So there will be some map like this, and the only question is to describe, and so is described the kernel of that map. And the kernel of that map, the way this the quantum the spin chain is going to come in is that the kernel of that map, this will be the beta equations for. So this in this quantum integrable model, there's the search for eigenvalues consists of two parts. First, you make some ansatz. Means ansatz is just a substitution translated from German. Means you try some form of the eigenvector. Depends on some parameters, which are they're called beta roots, and this will be k of them, and so this will be this x1 through xk, and then this eigenvector, this ansatz for the eigenvector is actual eigenvector if this xk satisfy some equation, some algebraic equations known as beta ansatz equations, beta equations. And so this somehow the basic observation. This was the starting point of Negrad-Shutashvili. You can compute. I mean, this it's not hard to compute the spectrum of. It's not very hard to compute the spectrum of quantum cohomology from abstract principles, especially for T-star Grassmannian. And you see that these equations that, well, I guess I kind of wrote the equations down, but I gave you the solutions of the equations. But you can write equations, and you see they coincide with these beta equations for the spin chain. And then you can. This is like this was the starting point, and we'll see it like this later. And so in particular, then you'll see this description of that I've presented here without proof. All right, now I think I've exhausted my 2 hours, and I'll stop here for today.